Hey, everybody. Thank you so much for joining us today. This is our final webinar in our Amp Up Our Devices, well, I guess Amp Up Your Devices webinar series, which is a series showing examples of how our Fusion AX system here at Protochips can be used to study nanoelectronic devices in situ within the TEM. My name is Jen McConnell. I'm the product manager here at Protochips. And thank you to those who are here that have joined all episodes of this series. I hope you've all found the webinars to be both educational and inspirational. If you've missed any of the episodes, please feel free to check out our YouTube page and look for the Amp Up Your Devices playlist to catch up on the other cutting edge research that was presented. You can also learn more about the Fusion AX system, which our speaker will be talking about today, and machine vision software that can be used with it, all on our website as well. So today we have an incredibly talented speaker who's not afraid to take on large challenges to help set the proper benchmarks to help lower the barrier to entry for future scientists when it comes to nanoelectronic devices and electrical characterization research. He's been known to build and modify equipment to test new concepts and really help drive these new workflows in the electrical characterization space. And so I'm really excited to introduce today Dr. Tolga Wagner from Hambolt University in Berlin. Before I go through his biography, let me do a couple of housekeeping items, and then I'll formally introduce him and hand the microphone over to him. So everybody's muted due to the audience size here, so and preventing any accidental interruptions. We will have a question and answer session at the end, so please enter any questions you have during the presentation into the questions box on the webinar panel, and then we'll do a back and forth with Tolga later at the end of his presentation. And then we do have a survey at the end that will pop up. If you don't mind taking 2 seconds to fill that out, we would really appreciate it. It will help us on future webinars. But okay, enough of that. Let me introduce our star and our speaker today, Dr. Tolga Wagner. So Tolga is a researcher at the Department of Physics at Hambolt University in Berlin with a strong background in it's a little early for this, methodological and instrumental development, specializing in ultrafast electron phase imaging. His research focuses on investigating dynamic processes in semiconductor nanostructures and operando devices. He graduated from TU Berlin in 2022, where he co-invented and developed time-resolved electron holography. His contributions to advancing dynamic electron microscopy were recognized with the Research Award from the German Society for Electron Microscopy in 2023, which is amazing. Tolga, thank you so much for being here today. I am going to hand the microphone to you. You can start whenever you're ready, and I'm going to drink more coffee so that I can improve my English.
Thank you, Jen. I will do that too. And of course, thank you for giving me the opportunity to speak here at your webinar series. I will use this opportunity actually to give something back to the community. This is the idea from my side, because I tried so much attempts being able to put biases on tiny TM specimens and failed so hard so many times. And my goal is to give someone who wants to start doing biasing a bit of a head start due to my mistakes, which I will show you today. Of course, I will also show you something about my recent research and will tell you something about time-resolved electron holography. But for a start, I want to give a very brief motivation, because what we are doing here, we are investigating stuff. For me, it's like semiconductor nano devices, which are basically always some kind of differently doped regions in a material, in a semiconductor material, and in between is an interface like a space charge region. And by applying an electrical bias from outside, we can change or redistribute the charge carriers within these regions or interfaces. By this, we can turn tiny devices on and off, for instance. And for me, doing dynamic investigations, always the question was, what is happening in between? I mean, we can use a biasing holder and switch states, but what's happening in between? Is the transition from one state to the other state some kind of random interaction of the charge carriers, or is it following some kind of rules? So this is the question. For me, the question is the journey of an electron or charge carriers, and the question is, can we image charge carrier dynamics going on to a transition state? So before I start the journey of an electron, I want to start my journey, because working in a community like the electron microscopy community is a great thing for me. And I, for my time here, got a lot of support from many different people, of course, involving the institutions I'm work in and with, starting from the TU with Michael Lehmann, where we developed this time-resolved electron holography technique, and a lot of biasing preparation stuff. We also developed at TU together with Dirk Berger from CELMI, or I got a lot of support at my new place here at Hambolt University from Christoph Koch, and of course from the IKZ guys, where we are building a new special dynamic operando lab in a close collaboration. Outside of Berlin, I got a lot of support from people who are also interested in biasing and electron holography, which is a lot. And last but not least, I'm very grateful for the support I got from the Protochips guys, because they were great help when it came to modifying some of their equipment, which is, I guess, not the normal case for TM investigations, but in my case, it was necessary, or just getting help with new chips and new chip designs, which was a big help for me in my research so far. So let's start. Before we can do any kind of measurements or investigations, we need a specimen. That specimen must be prepared. And for everything in this talk, I'm focusing only on membrane-based, on MEMS-based systems. So we are only talking about biasing holders where we use MEMS chips, it's support carrier chip for the specimen, not the ones with the SDM tip. Because for me, it was always important to have a reliable, proper contact of the specimen regarding the dynamic investigations. So everything we need is 2 electrical contacts, which are given by the MEMS chip. Then we need to put something what we want to investigate onto these contacts, thin it down until it is electron transparent, and then, of course, by using FIB metal deposition, creating proper contacts. That sounds easy. When I started doing biasing experiments and we thought about it with Dirk Berger from CELMI, we had one problem. All these MEMS chips featured a supportive silicon nitride membrane. So the gold pads were on a membrane. And a membrane means if I want to do like thinning of a specimen, I need either some kind of elevation, so some kind of support blocks to elevate the specimen that we can thin it down with the FIB machine. Or what we also tried, we tried to put the specimen with an angle onto the chip so that we can like change the angle of the stage in the FIB and thin it down. Or even, and it's the most ridiculous one, we tried to build up front a specimen which has some kind of a bench structure. And I want to pick a bit more on the last example to show how ridiculous times were back then. So in order to really investigate a nanostructure like this, where we know, okay, we have this Wechsel structures where we have a laser inside and we want to switch the laser within the TM. So we thought it is reasonable, because of the membrane problematic, it is reasonable for us to deposit a lot of platinum onto the structure, then cut it out in a bench style, and then for like putting it onto the contacts, it was also necessary to modify the MEMS chip so that we have the right geometry to do our experiments. And back in the day, this process seemed kind of reasonable to me and also to Dirk Berger, because it was the only option for us to do so. And please keep in mind, this preparation process took about 2 days. So we needed 2 full days to prepare one specimen to come up with something like this. And here you see the next problem. You have this platinum halo everywhere, and we had shortages, and we cut them away and again and back and forth. So it was very frustrating to know you have to spend like 2 days preparing these kind of lamellas for investigations. And it was very time consuming, and not every lamella was a success. So more or less every 5th lamella was a success. So it was very frustrating in the time beginning doing electrical biasing experiments. And then something happened. In the same time, I got in contact with Protochips, and also a colleague of mine, Rémi Bétier, was doing his PhD thesis, and they together co-developed something which for me was a real game changer. It was the first MEMS chip which was not membrane based. So a chip without the silicon nitride membrane. It was basically, here you can see it, it is a slot in a silicon die, and you have your contacts on the top, and they're physically separated. So there's no way of shortage, and from the front side, you can easily mill the specimen. So for me, I thought, okay, every problem is solved. We can now do proper biasing. And at the same time, the chip was developed, and I got my hands on a very early version of it. I was modifying for my research an old Protochips Aduro single tilt holder to make it usable for radio frequency investigations. And I thought, okay, I have now this Aduro holder, and the chip should fit in the Aduro holder. So I tried it and found out that the Aduro holder was only meant to fit with the older membrane-based chips, because the membrane-based chips were double the length, and you can grab them with your tweezers from the front, and you can load your sample from the front. So it was not very easy for me to put these new chips into my holder, which is the base for all my research. So I talked to the guys from Protochips, even talked to John. And after arguing and discussing a few steps, I came up with a solution. So the solution was drilling everything away, which is like not needed for me. And by that, I had actually a very, very tiny free space here where I can put directly the new chips from the front side. So this was my experience with Protochips. It was basically, you know, your old holder, I need to mill it down. And they said, yeah, why not? Try it. And it was very, very okay. So coming back, now everything is fitting, so we need to prepare a sample. And for me, I grabbed a diode, a simple silicon diode, and the goal was to go from millimeter size to nanometer size to bring it in between these freestanding contacts of the chip. And the start was actually very simple, just grinding it down using this tripod or T-tool to grind the diode down. And then I faced my first problem without even being close to the TM. These PN junctions in silicon are not very visible. This is actually the reason we need these special techniques to make them visible in the TEM. But out of the box, the question was, where is the PN junction? And there is actually a rather easy way to find out. If you have a fit machine, you can connect a key sleeve to your micromanipulator, and by putting the micromanipulator to one side of the PN junction and applying a bias, you can really easily make them visible in your secondary electron detector. This is, of course, called voltage microscopy, and it's based on surface charging, which is happening here, and there's a lot of theory behind it. I actually tried to turn this into a very simple biasing experiment by trying out how the contrast changes over the applied bias. And if you look how the contrast changes with the applied bias, you can clearly see that something is happening if you apply a reverse bias to the diode. So the diode's still doing diode things, which is always good. And for us, it was, okay, here somewhere in this region, we can get out our material for the TM lamella. But keep in mind, it was pretty clear that the diode, so the TM lamella, will be very big. So this is not a semiconductor nanostructure, but a semiconductor device anyhow, and we wanted to start. So we started the preparation. And it was straightforward, simple preparation of a TM lamella, lift out, and then transferring it onto the chip. We needed, actually, because the PN junction was so wide, we needed to make the gap a bit wider. But in the end, we came out with a very, very flat lamella between two freestanding electrodes. And if you keep in mind and look at the last two images, this is actually pretty close to the state we wanted in the beginning. So if you want to try biasing and your aim is to do biasing with targeted devices, so cut out a PN junction or transistor or something out of a chip and putting it between two contacts, please do not make the same mistakes that I made. Just go grab your FIB optimized E-chips and start without the membrane, because the membrane was like taking me at least 3 to 4 years to figure out how I can eliminate all these problems. And in the end, the only solution was to get rid of the membrane. So this is the first part, more like focusing on what mistakes you should not make doing biasing experiments. Now we can go to the instrumentational part and the method part. So we have a specimen prepared with a PN junction, and we can switch it from outside using our Protochips biasing system. Now the next question is how to make this PN junction visible. And for this, I'm using electron holography. Electron holography is a rather simple technique in a TEM. The only difference to standard TEM is actually that there is an electron biprism, which is used to overlap two partial electron waves. One electron wave is modulated by the object, and the reference wave is, in the best case, unmodulated. By this, an interference pattern is produced on the screen, where you can see in the interference pattern basically two things. One thing is that the visibility of these fringes, these are the hologram fringes of this interference pattern, that the visibility of these hologram fringes is changing within the image. So this changing of visibility is correlated to an amplitude modulation of the electron wave. And then there are places where the fringes are shifted. And this shifting of the interference fringing is correlated to a phase modulation. So electron holography is capable of solving the phase problem in TEM. And to do the electron holographic reconstruction, we do a Fourier transformation of the image. So the Fourier transform will show these sidebands next to the autocorrelation of the image. The sidebands correlate to these hologram fringes. And by reconstructing one of these sidebands, we get access to amplitude and phase modulation of the electron waves involved. The amplitude information is, at least for me, rather boring. It's the same thing I can get out of the intensity much easier. But the phase modulation is very interesting for me because the phase modulation is actually directly correlated to the projected electric potential. So if I want to look at a specimen which features interesting electric potential distribution, like the semiconductor nanostructures, I can directly make it visible, at least their projection, by electron holography. And this is good for static biasing experiments, but for us it was like the question, if we want to look at dynamic processes, how can we take this a step further? Is it possible to do time-resolved electron holography? And of course, the usual suspects come in mind. So first suspect is we can use a pulsed illumination, like a stroboscopic illumination or a photoemitter, like everyone else does. The problem is, if we just think about it, we are pulsing the whole microscope, so also the specimen. This means within the pulse, there will be some charging effects of the surface, and this surface charges will have a dynamic, so a transient time. The transient time is, of course, in the same time scale as the process I want to investigate, the dynamic of charge carriers within the material. So constantly charging and discharging the surface of my specimen will produce a lot of problems. So to do nano to picosecond temporal resolution with electron holography and trying to do that with a pulsed photoemission is, I guess, not the smartest way. The second option is, of course, we can use a very fast detector. And if you look at modern ultra-fast detectors, we are speaking about timescales in the nanosecond regime. The problem here is, obviously, we will produce a lot of data. And in order to go really down to nanoseconds, we will reduce the number of pixels we can use. And by this, we will have a big problem because we need all the pixel we can get to resolve these fine fringes for electron holography. But we thought about a different thing. Basically, electron holography is an interference-based method. And for interference, it is rather easy to destroy the interference. Actually, all you need is shake the microscope. And basically, what happens is that you will have a slightly different ray path, and by this, your interference pattern will be a bit shifted. And we can do this in a rather elegant way by introducing a dynamic phase shifter, which is nothing more than an object within the column, which is introducing some kind of very tiny tilt to the electron beam. And by this tilt, we will produce a lateral shift of the interference fringes, which will in case give us a constant offset in phase. And if you think about, the easiest way to destroy a fringe pattern is overlapping a lot of individually shifted fringe patterns by, for instance, connecting to the phase shifting device some kind of a signal like a noise signal. So if we apply a noise signal to this phase shifting device, we can get rid of the interference fringes, and for that we'll have no sidebands in the Fourier transformation. So in a real experiment, this looks something like this. This is my camera when everything is like constant and we don't apply a signal to the phase shifting device. And if we apply noise to the phase shifter, we come up with something like this. So we get rid of all the holographic information. If we now start an exposure where the phase shifter is used to destroy the interference pattern, we will record no interference information. But for a brief period of time, which we call the gate, we can stop destroying the interference pattern. And by this, we will gain holographic information over this time interval, over the gate. And then for the rest of the acquisition, we can then again destroy the interference again. What we will come up with is actually a very, very bad interference pattern, because a lot of it is without interference fringes. But if we think about periodic processes, we can actually do this experiment a few million times. And by that, we can gain signal to noise and then come up with a reasonable, usable hologram again. So this process of letting interference only happening in a very short time period can be synchronized to a biasing holder. And by looking only at distinct time positions, we can then sample the whole period of a process. This is the basic idea of interference gating, or iGate, for time-resolved electron holography. Maybe one or two words to this dynamic phase shifting device. It always sounds very fancy when people telling you we use this and that. In a TEM, everything is producing phase shifts. So actually, if you want to introduce a small amount of phase shift to, for instance, destroy the interference pattern, it is rather easy. You just go look where you have an aperture holder which you are not using, and then by gluing a cable in, I mean, you need to drill a hole and then you can glue a cable in and just use the open end of the cable. Basically is everything you need. You then can call it a microwave cavity and go to gigahertz, but basically this is what we are using at the moment and experimenting with. Rather simple aperture holder, which will give us the possibility to go up to gigahertz. And by this, we are currently in our setup realizing time resolutions down to 2 or nearly 1 nanosecond. Anyway, going back to our diode. We now know the method, electron holography, and it is rather easy. We know that the diode is now in a shape where we can apply bias to. And before we start our experiment, we should think about what are we expecting. We know that we have some kind of material featuring a P side and an N side, and in between there should be some kind of potential distribution, which is correlated to the diode. And then we come in with a plain electron wave. And according to the theory, the electron wave will be modulated by the potential distribution. So in the end, in the projection, we are expecting for this lamella, which is indicated here, something like this. And because it's a rather big lamella, we are talking about 20 microns here. We did go to Forschungszentrum Jülich and did an experiment on their holo machine for a static measurement. And the experiment showed over the same field of view something like this. So the first question for us was, what is this blob? So, and before starting putting some like explanation into it and start to find out if there are some trapped charges or whatever, it is always good to go and model your problem. And this is what we did. Again, we have a very huge gap of 20 microns here. So if you want to do numerical modeling of such a big volume, like we model something like 50 by 50 by 50 microns, it is very hard to do it with something like finite elements. So actually a former student of mine, Hussein, came up with a very simple and intuitive model for potentials. So we used this one actually with a very simple initial potential, and his model is using like an adaptive Gaussian kernel to like approximate the potential distribution, very similar to a heat kernel. And with this, we came up with the modeled projected potential for like very big area. But then for our experiment, we can actually model also the region where the reference wave is going through. And this is actually a big problem for electron holography. You have always to keep in mind what is your reference wave doing. In theory, it is always assumed that the reference wave will be unmodulated, but in reality, we are facing a lot of stray fields due to our specimen. And so it is always the difference between reference wave and object wave we are measuring in the experiment due to the superposition of two electron waves. So if you keep this in mind and look at the difference by subtracting the reference wave from the object wave, you come up with a model of your specimen by only making very simple assumptions, which is rather in a good agreement with our measurements, with our biasing measurements. And if you see, even we took line scans, and the line scans seem to agree very much. By the way, what you're seeing here is the normalized reconstructed phase. By this, I mean we will always subtract a 0 voltage measurement to get rid of a lot of problems we had within the specimen due to dynamic diffraction. It was necessary for this object. It is always a good measuring tool to look at differences, because by this you can to be sure that you only see effects of your applied bias. So everything we see here is an effect of the applied bias to the specimen, and also in the simulation we do the same thing. We always get rid of our 0 voltage measurement by subtracting it. And if we look at 0 volt, the normalized phase should show nothing because we are subtracting two different 0 voltage measurements. At 1 volt reverse bias, we can clearly see that there is a phase progression between P and N side, and it gets like higher for more reverse bias, which is in general agreement with the expected behavior of a PN diode, which is reverse biased. So our experiment together with the modeling shows that we understand what is happening in the specimen. So now coming to dynamic measurements, we have not only the tool to do the static electron microscopy, electron holographic investigations, but also the dynamic ones. Here we came back to Berlin, at TU Berlin, where the tight microscope with the ultra-fast setup stands. So basically an aperture holder with a cable. And the field of view for this is a lot smaller. It has something to do with the camera they have in Jülich. It's a very good camera, and we don't have a very good camera in Berlin, but also to get the needed fringe contrast for the dynamic measurements, we need to make a trade-off between field of view and fringe contrast. So for the time resolved measurements, here is one frame out of the measurement correlated to a like 1 volt reverse bias, taking at 150 nanoseconds of a period. So we applied a square wave between 0 volt and 1 volt reverse bias. So the device is constantly switched between unbiased and reverse biased state. And we do that at a repetition rate of 3 megahertz. So a period of switching on and off, or reverse bias and unbiased, will take 333 nanoseconds. And here is a frame, a time frame at 150 nanoseconds, which is correlated to minus 1 volt bias. And here is a time frame correlated to the unbiased situation. And again, also the dynamic measurements are normalized with a 0 voltage measurement. So we can also correlate this again to the things we saw before, just in a smaller region of the sample. And it is in good agreement. So we see both states, unbiased and reverse biased state, and we can understand it. What we also saw in Berlin was, and also in the static measurement, but I didn't show it here. If we do a line scan in y direction, we can see as soon as we have field, because it's still a normalized measurement, we will see that there's an increase in phase shift towards the edge of the specimen. So the phase is increasing towards the edge of the specimen, which gives me, based on experience, some kind of vibes that we have introduced other potentials near the edge of the specimen. And I assume it should be produced by the gallium ions used during the FIP preparation, but this is something we should keep in mind. So there is something happening out of static measurements. We see it already towards the edge of the specimen. So having now the opportunity to look at all these frames, we can basically do a very, very intuitive analysis of the switching behavior by watching a little movie. And this was, once again, I mean, the goal of my research, to come up with a tool, time-resolved electron holography, which makes it possible to do real-time investigations of like charge carrier dynamics in semiconductor structures. So here's the movie. You can see we start with the unbiased state, and then the phase slope is coming in, and then it's leaving again. Now, just let's play that in the background. It's not important, but what we know is that we have different parts in our specimen, different regions. So the first region is deep inside the space charge region and as deep as possible for this field of view inside the specimen, according to the edge of the specimen here. So we have region 1, which is deep within the space charge region. Region 2 is very close to the N side of the silicon diode. Region 3 is close to the space charge region, but very close to the edge of the sample, which will maybe feature some different behavior. And the fourth region is again in the N side of the silicon diode and very close to the edge of our specimen. So if we look at the phase progression over time for region 1, we can clearly see some behavior which is expected by a diode. So we see that switching into reverse bias, given that we have an external field applied, is happening rather fast. So we're talking about some 15 to 20 nanoseconds, the switching process. So it is very quickly switching into reverse bias condition, but then again, out of back to the unbiased condition, it takes a lot longer, nearly 4 times as long. So this is something we expect from a diode. This is basically the diode behavior we expect from this special diode. It's an ultra-fast rectifying diode, and it correlates also to the behavior we measured from the whole device. So as far as it goes, we are in good agreement with everything we understand from diodes, and we basically build something which is similar to an oscilloscope, but a lot more pricey. But if we look at the second region, for instance, we see that already we have decreased the switching times, because in the N region, we expect the diode more to behave like a metal and not like a diode. So everything we can see here now is actually also explainable by theory, but in contrast to the oscilloscope, we can do now localized measurements. So we can track the progression of the projected electric potential during these switching processes in a localized manner. So we have basically an oscilloscope with very, very tiny nanometer probes that can probe nanostructures within these semiconductor materials. So for the third region, which is very close to the edge, we see a completely different switching behavior. We actually see that switching into reverse bias condition stays nearly the same, but then again going back into unbiased condition happens a lot faster. And more or less the same is visible for the part here, where we are also close to the surface, but more on the N side of the silicon diode. So the times go shorter compared. And actually having a shorter transition time is something we expect to happen if we introduce gallium ions close to the edge. We have new conduction pathways. We have also more recombination centers. So there's a lot of stuff happening, and I don't think that this special diode has these features. I'm aware of that we introduced these features by preparing it. Anyway, I guess this showcases that dynamic operando investigations and dynamic operando electron microscopy is a thing we can use to characterize and analyze these nanostructures, these tiny working devices within the TEM. And this is something I started a few years ago, and I'm very, very grateful that everything worked out so far. So let's come to the twist. The title was Biasing with a Twist. We can actually visualize this directly in the frames. If we look at everything that's happening here, and we see that from frame to frame to frame, we see changing of these equi-phase lines. We can track the first line and actually see that in the progression in time, this line is twisting. And this twisting motion means nothing more than the decreasing space charge region, which is like evident here in the phase, which is correlated to the projected potential within the space charge region, is actually happening on different timescales in respect to the distance to the edge. So in the same amount of time, the equi-phase line moved nearly double the distance closer to the edge, which means, of course, that the involved charge carriers, which are like the source for the potential distribution, also must have been moving double the speed near the surface of the specimen. And with this, I'm all ready to conclude my webinar here. And first of all, I mean, dynamic operando electron microscopy is something that seems to work, which makes me very happy because I worked a long time on it. And actually, we did not stop. So at the moment, we are constantly further developing dynamic electron holography, both at TU Berlin and here now at HU Berlin. But on the same time, here at HU, together with IKZ, we are working on dynamic DPC, where we building a new detector, a new detection readout, and trying to go to similar timescales we are achieving at the moment with dynamic electron holography. The other problem which we saw for electron holographic investigations was, of course, the modulation of the reference wave, which is at the moment very good to handle if we have a model of our specimen, but there are also progresses which are running in the background. So we came up with something called the reference window, where we cut in a tiny window to kind of shield the reference wave. This is a very promising approach, but for me, the biggest elephant in the room is the big distance between the freestanding electrodes of the biasing chip. So even I think that, I think that the FIP optimized E-chip is the best thing that happened to electrical biasing so far, if you're really interested in investigating devices. But I find that there must be more. We need shorter distances between these freestanding electrodes, and we need to find a way that these electrodes are more adapting to our specimen and not that they're giving us like the restrictions for our geometry of our specimens. And I hope we will find a way together as a community. And with this, I thank you all for your time. And also, if you want to contact me, if you have any questions or questions regarding biasing or dynamic investigations, or want to test something out, please contact me and write me an email. So thank you.
Thank you so much, Tolga. Great presentation. Really appreciate it. Really great videos that you've gotten there too. Let's see here. Sorry, I had to move rooms and it's disheveled me a little bit. So we've got some questions here. Let me start going through them, and any of them that we don't get to, we'll make sure to connect you to the scientist that was asking them offline. And if you don't mind answering them there, that would be great. If anybody does have questions that they haven't entered into the questions box yet, now is a great time to do it. Okay. So the first one here, dear Dr. Tolga, how much voltage and current did you use to thin the lamella when you finally processed it so that it could reach nanometer thickness? And how much thickness did you cut off at that time?
As I mentioned, first of all, thank you for the question. As I mentioned, the preparation work was done mainly by Dirk Berger from Telmi. And we tried different approaches. We tried to leave the acceleration voltage of the ions very high, and we tried to reduce it. And in both ways, actually, regarding the projected potential, we came up with the same results. So the integration of the gallium ions, and this is very complicated, so sorry for me trying to find the right words. As far as we understand right now, you can reduce the surface amorphization if you choose the right parameter and go to lower acceleration voltages and also lower currents. So this is something you can do to reduce the surface amorphization, but the modulation of the electric behavior of the device is not necessarily correlated to the thickness of the amorphization layer. So independent of different thick amorphization layer, we found that the altered potential or altered projected potential is going micrometers into the specimen. And what we are now trying to do in collaboration with IKZ, we are trying to make use of their new plasma FIP and hope that we can get rid of the ionization problematic with this approach. I hope this was okay.
They responded with thank you. So I think that answered the question. There was another question that was sort of along the same lines. I think you may have covered it, but I'll ask it anyway. And it was referring to the thinning of the lamella, and were there any concerns that how thin you made it affected the phase shifts that were measured or the measurements that you were making?
Yes, general for electron holography, you should aim at lamellas around 300 to 400 nanometers. If they are too thick, you're suffering from other problematics like dynamic diffraction. If they're, and of course, reduced fringe contrast. If they're too thin, then you have not much of the potential distribution left within. But these are all investigations that were done like several tens of years ago.
I don't think you were alive several tens of years ago. So next question is, how do you differentiate between phase shifts caused by electrostatic potentials versus magnetic fields in the electron holography?
Yeah, of course, in general, you have both. And for my work, it's rather easy for me to assume that I ignore the magnetic part of it, because the magnetic phase shift should be at least very, very small compared to the electric one. But if you have devices they drive, which drive high currents, of course, you need to include your magnetic phase shift. And then you need to find ways where you can like see differences and make like calibration or other type of measurements to correct for them. I mean, in magnetic investigations, always the sample is flipped upside down to get rid of the electric part. Maybe we can do something similar here. Then, of course, we need a new chip, which is flippable.
Always a discussion to be had, right?
Yeah.
Two more questions so far. If anybody else has any questions, go ahead and throw them, submit them to the questions box. Have you combined your holography results with other techniques such as EELS or EDS or any, I guess, other techniques? Yeah, EELS or EDS is what they have listed. Any other complementary techniques?
We actually used yields for just thickness measurements and compared this to the thickness we measured with electron holography, and within 2 nanometers or so, they agreed, which is always a good thing for me. That tells me that electron holography, as long as you know what your reference wave is doing, seems to work. That's very good. And at the moment, we are comparing it to other STEM-based technique like DPC. So we are working on a collab on a on a combination of DPC and holography in ultra fast. Of course, a lot of people have compared DPC to holography. Benedict Haas did a very, very good paper on it. So we are trying to combine it with different techniques. But for me, most in the case, I'm interested in like phase imaging and the imaging of the derivatives of the phase of an electron waves.
Perfect. Perfect. And the last question I have here for you says, what are the spatial and phase resolution limits of your holography setup?
Oh, thank you. That's a very, very interesting question. I mean, the setup itself is designed. We have a very special machine at TU Berlin. The setup is designed to do atomic resolution, and it is rather phase sensitive. So for my experiments, it was not so necessary, because I'm looking at devices, even with the nanostructures, I have field of views of like 200 to 500 nanometers. So the spatial resolution in general, in my case, is somewhere below 10 nanometers. This is the spatial resolution, but it's changing the instant if you use a different detector. So holography is capable of doing atomically resolved like investigations. There are a lot of publications about it, even from Michael Lehmann. And the phase sensitivity, this is something that needs to be discussed a lot longer, and is not to be cleared here. So we suffer from a lot of phase noise because we do time resolved experiments, but then again, we take a lot of caution to at least correct for that a bit by doing a lot of measurements and averaging them. But the phase resolution I have in my measurements, I really don't know at the moment, because the phase resolution is so much better than the signals I'm measuring. So I did not care at the moment. I hope this is okay.
Yeah, I'm sure. That wraps up the questions that we had for today. If anybody else has questions, I don't know if you've got you've got your contact information here. So Tolga, you can reach out to Tolga directly. I'm assuming that's okay, Tolga?
Yes, please.
Perfect, perfect. Thank you so much again, Tolga, for a wonderful presentation. It's always interesting to see where your research is now, as you've been trying to lay the groundwork for this technique for quite a while now. So made some
Thank you
amazing
for having me
progress.
here.
Of course, anytime. And thank you everybody for joining. I hope you all have a great rest of your day or your evening, wherever you're located, and we'll see you again soon. Thank you.